topic 4.5. We're going to be graphing rational functions. And here we have a rational function, and I want to make this into a complete, we have a rational part and a non-rational part. I want this all together to be a rational. So I'll need to get common denominators. So I'm going to convert my 1 to an x over x. It's still equivalent to 1, but now it has the same denominator as 1 over x. And now I'll combine those, and we'll have x plus 1 for the numerator and x in the denominator. Now, from here, I'll start finding my parts and pieces. First, let's find the x-intercept. The way that we find the x-intercept for a rational function is by setting the numerator equal to 0 and solving. We'll have x equals -1. So x equals -1 is the x-intercept. Next, we'll find the y-intercept. We find the y-intercept by placing 0 into all the x's. Since here we have 0 in the denominator, this will be undefined. Therefore, there are none. Or there is no y-intercept. Next, we look for the vertical asymptotes. We find the vertical asymptotes by setting the denominator equal to 0. Vertical asymptote is x equals 0. That's a vertical line. That's right here. Okay. Next, we find the other asymptotes by using long division. So y is going to equal, let's see, x divided into x plus 1. Okay, from here, we'll say x divided by x, which equals 1. And then we'll multiply 1 times x, which is here. Then we'll change the signs to negative, and then add our terms. These will cancel, and we'll get 1 left. Since 1 is a remainder, we do not use the remainder. We only use the portion that's here. So y equals 1 is our asymptote. Y equals 1 is a horizontal line. So I'm going to put a horizontal line right here, which represents y equals 1. Okay, now from here we're going to draw our graph. And the graph will be drawn about the asymptotes. Now, the graph will be either just above this asymptote or just below. The way that we know if it's just above, in order to follow the next asymptote up, or below to follow the next asymptote down, is to look for paths that include intercepts. This path has to include the intercept -1. Therefore, I know it will be below. Okay. Next, let's start from the other side. We're either above this asymptote or below the asymptote. A path above would climb up the asymptote, a path below would climb down the asymptote. In order to climb down, we would need an intercept. Since there are no intercepts on this side, we're going to choose a path that would not include intercepts. So the path will be above. And that's our graph. Next, we're going to be graphing f of x equals x squared all over x minus 1. We'll put the graph here. And the first thing we'll look for are the x-intercepts. We find the x-intercepts by setting the numerator equal to 0 and solving for x. And here we have x equals 0. Next, our y-intercept. We find the y-intercept by setting all x's to 0. So we'll get 0 squared all over 0 minus 1. 0 over negative 1 will be 0. So our y-intercept is also 0. Next, our vertical asymptotes. We find the vertical asymptotes by setting the denominator equal to 0 and then solving for x. X will equal 1. So we have a vertical asymptote here of x equals 1. Now, our other asymptotes. We'll find those by using long division. This will be x minus 1 divided into an x squared. Okay, so let's begin by dividing x squared by x, and we'll get x here. Then I'm going to multiply the answer x times both these terms, and we'll get x squared minus x. Third step, I want to change the sign, so take the additive inverse. So this positive becomes a negative, and this negative becomes a positive. Then I'll combine like terms, and we'll get an x here. So next, it'll be this x divided by x, which gives us 1. So 1 is our next term. Then I multiply 1 times both these, which will get x minus 1. Change the signs from a positive to a negative x and from a negative 1 to a positive 1. Combine the terms and you get 1. Since we do not use a remainder, this is our other asymptote, y equals x plus 1. Now that's a linear equation with a y-intercept of 0, 1. So we're going to go to 0, 1 right here, and the slope will be 1 over 1, so I'm going to rise 1 and run 1, rise 1 and run 1. And this becomes my other asymptote. Okay, so now we have all 4 parts in. I'm going to graph. Now, let's begin with this. I'm either going to come down this asymptote or travel up this asymptote. Well, which path would include the intercept? Well, the path down here would finally get to the intercept as opposed to this path. So we're going to use the one coming up and go to the intercept. And once we're there to the intercept, we notice that there's a multiplicity 2 on that intercept. So we're going to get a bounce. So it's not going to go through. And then it just follows this asymptote getting closer and closer. Now let's go to the other side of this vertical. We're either going to be climbing down or climbing up. Well, the path climbing up would require an x-intercept, and there are none. So I'm going to choose a path that does not need the x-intercept. So I'm going to climb down and then follow the next asymptote. And so this is the final graph. Now we're going to graph the rational function x squared minus 9 all over x plus 3. Now, we're not going to look for the 4 pieces just yet because this simplifies. And when a rational function simplifies, the simplified version will actually create the graph. So, to simplify this, I'm going to factor the numerator into x plus 3 times x minus 3 all over x plus 3. This simplifies to x minus 3. Now, the graph of this, of the simplified version, will give us the actual graph that we're looking for. Okay, so we have y equals x minus 3, where the y-intercept will be 0, negative 3, and the slope will be 1 over 1. So rise 1, run 1, rise 1, run 1. Now, this is the graph of the simplified line. One thing we're going to watch out for is that the original problem has a domain restriction. The domain restriction is this: x plus 3 cannot equal 0, which implies x cannot equal negative 3. Well, on this graph, when x equals negative 3, that point has to be missing. And to find that point, where x is negative 3, we're going to put negative 3 into this equation right here. And we get the point negative 3, 6. This point will be removed. And I'll put an open circle at the point negative 3, negative 6. Because negative 3, negative 6 does not exist in the original domain. Even though it exists in the simplified equation, it does not exist in the original domain. What we call this is a removable discontinuity.